Namaskar, my dear friends. Let us talk about network theory, that is nothing but circuit analysis. So we'll see each and every topics related to gate in this particular subject, that is network theory. So let us start with electric network analysis. All right. So what we are going to talk about is we'll first talk about what is my network and circuits. Okay. So there are two terminologies that you can see here. We have network and circuit. So somebody tells it like, okay, we have something like some electrical elements are there that can be called as network or circuit. What are the different situations in which you can tell them, right? So as you can see, you have to write it down as any arbitrary interconnection, any arbitrary connections of electric element constitute a network, constitute a network that may or may not, that may or may not have closed path. Understood? So like you can see that we have, let us say, inductors, one resistor is there, one voltage source is there, like this. So this can be called as network. Understood? So what I'm going to tell you one more thing before you start your complete, syllabus for this network theory is you have to follow only the class. We will be talking about theory, practicals, and all the electric, gate questions that is needed. Those questions also we will see. So it will be a complete package where you can think of, gate and think of this particular training sessions. That's all. Okay. So next is we will talk about circuit. So what is that? However, if the interconnection have at least one closed path, if the interconnection have at least one closed path, then it is said to be network as well as circuit both, right? So then it is both network and circuits. So at least one closed path is there, then only we can tell that that is a circuit. So it means you can say that all the circuits are network, but all the networks may not be circuit. Why? Because the open ones cannot be called as circuit. So you can tell that all circuits are network, circuits are network, but all the networks are not circuit. Understood? So you can see, like let us say we have a resistor, one more resistor is there, and then we have a voltage source, and then we have one more resistor and then capacitor. Okay, and then it is connected like this. So as you can see that we have this closed path, this closed path. So this can be called as network and circuit. But if I tell you this, let us say we have voltage source, we have one capacitor, one resistor, and it is this. So this will be only network. It won't be circuit. Understood? Now we have two terminologies that is called as analysis and synthesis. Okay, so what is analysis and what is synthesis? So these terminologies are very important. That's the reason I am telling you in the beginning itself. Later on we will have lot of other parts that is there related to GATE. So if you have a good understanding about these two terminologies, it is more than enough for me to tell you everything about GATE questions, GATE syllabus that is being asked. Okay, so GATE is all about concepts. There is nothing to memorize. All right. So you can say that if you want to find a response, okay, like from a given interconnection, finding the response is analysis, or solving the circuit is analysis. Okay, finding the response is analysis. So it will be actually unique, right? However, we will design something. Okay, so designing the system to satisfy some input output relationship. Okay, satisfy some input and output relationship is synthesis. Understood? It means you can say that finding the response is actually unique, right? The analysis is unique. However, synthesis can be multiple because you have multiple ways to satisfy the same input and output relationship. So you can write it down that as well. So you can say that analysis means unique solution and synthesis multiple solution. Okay, for example, let us say we can say amplifier design. Here in the analysis part we can say, for example, solving a circuit. So let me give you an example so that you can have a proper understanding. Let us say we have amplifier like this, minus plus, we have this. So this is my V input and this is my, let us say 1 kilo ohm, and this is, let's say 3 kilo ohm, and this is, let's say, output. Let's say V input, I'll put it as, like 1 volt. So what will be output? So V output is nothing but minus R2 by R1 into V in, and this will be always constant because my R2 and R1 is like unique value. They are defined value. So we can say minus 3 by 1 into 1, that is minus 3 volt. Understood? Similar to that, if I want to design, okay, let us say design inverting amplifier with gain equal to 3. So what will you do? You can say that, let us say you are designing this minus plus and this is my V in, this is, let's say, R1, this is my R2. So this is my V out and this is going to be ground. So can you tell me, gain is 3, right? So gain is nothing but R2 by R1. So it can take any value. Let us say R2 is 30 kilo ohm, R1 is 10 kilo ohm. Like it can take 30 kilo ohm by 10 kilo ohm. It can also take 3 kilo ohm by 1 kilo ohm. It can also take 300 kilo ohm by 30 sorry, how much it is? 100 kilo ohm. So there are n number of values which will satisfy the same gain. That's the reason this is synthesis. So this one was analysis and this one is synthesis. Understood? Now let us see about the syllabus that we will be, seeing. So what we'll do is we'll try to understand what is the syllabus for this network theory. Or sometimes it is said to be circuit analysis. Okay, circuit analysis. So basically what you have to do is you have to note it down what are the different topics that we will be covering during this complete gate syllabus. Okay, so very first thing that we will do is DC network analysis. Okay. In DC network analysis we will have a lot of things. Let us say number one, we will have fundamentals, and we will have DC network theorems. Okay, there are a lot of theorems that we'll talk about later on. So basically these two topics will be associated with resistive network analysis, like resistances will be involved. Okay, so resistive network analysis. Hope you have a good understanding now, right? Then next one we will talk about capacitors and inductors. So there are a lot of circuits that is there associated with only capacitors and inductors, and these are being asked in gate examination. Okay. Next one we'll talk about first and second order circuits. Okay. First and second order network analysis. Network analysis. Then after this we will talk about AC network analysis. So DC is fine. Okay, DC is fine. Then we'll talk about AC network analysis. In that we will see first sinusoidal steady state, steady state analysis, and then we will talk about resonance. Resonance circuits are very important. Okay, and then we can talk about two port networks. Okay, two ports. This is very easy, however it's very important. And in AC network analysis actually DC will also be involved. That's the reason we are telling it AC analysis. Okay. So why don't we see what we are going to talk about fundamentals. So we list out the topics under fundamentals. Those are the things that we'll see, right? So let us say we are going to talk about fundamentals in circuit analysis. So under this we will be talking about lot of topics that is going to be, let us say, what is the condition for current flow. Then we will also talk about basic electrical quantities like current, charge, all this voltage, everything. The basic electric quantities. Next, we'll talk about mechanism of electric energy flow through conductors. Okay, like what is the methods or what is the mechanism that is involved. Mechanism of electric energy flow through the conductors. Then we'll talk about power conventions. What are the different conventions that is followed to calculate powers? And in that only we'll talk about Teligens's theorem, which is very, very powerful. Understood? Next, we'll talk about resistance. Resistance is very, very important topic. That's the reason we will separately deal about this particular resistance. Then we'll talk about electrical energy sources like voltage source, current source. Sources. Then we'll talk about what is node, branch, mesh, loop, all these things. Node, branch, mesh, and loop in a circuit. Okay. Also, we'll talk about Kirchhoff's law. Okay. There are two laws like current law, voltage law is there. Okay. Then we will also talk about circuit solution by inspection. First of all, we'll try to solve by our heat and trial method. What are the different techniques to solve a circuit? So circuit solution by inspection. Understood? Next, we'll talk about series interconnection, parallel interconnection. Okay. So series interconnection and like voltage dependent sources or like voltage division resistance kind of thing. Then we'll talk about parallel connection, parallel interconnection. We will talk about resistance reduction techniques. This is very, very important. You can mark it because we are getting a lot of questions that find the equivalent resistance of a given circuit or given networks. Okay. Resistance reduction technique. Then we'll talk about source transformation, how to transform the sources voltage into current, current into voltage. This is very, very helpful to solve different kind of questions. Okay, that is being asked in GATE. Next, we'll talk about mesh analysis, nodal analysis that you would have understood, like how to solve circuit using mesh analysis. Then node voltage analysis kind of thing. So that is called as nodal analysis. So these are the different topics that we will cover under fundamentals of electrical networks. Okay. So let us talk about one by one each one of them. Okay. So let us start. So what is the first thing that we are going to talk about is let us start with condition for flow of current. Like what is the different conditions that will cause a current to flow? Conditions for current flow. So can you tell me what are the different, like reasons current flows, right? So let us say you can say there are, like some necessary and sufficient conditions are there, or may not be possible that it is not a sufficient condition, but we can talk about that. So you can take it right down like this: the necessary but not sufficient conditions. Okay. Conditions for current flow A. We can talk about there should be at least one independent source. Without one independent source, current cannot flow. Okay. So there should be at least one independent source. Understood? Next is we will talk about there should be at least one closed path as well as return path. Okay. Because without closed circuit the current will not flow, it will be open, right? So there should be a closed path as well as a return path, I mean ground kind of thing. Okay. See, you can say that a network doesn't have independent source, then when a network, I'll write it down network like this. Okay. Network doesn't have any independent source. I'm telling you that independent source is needed, right? Now, what if independent source is not available? So we'll talk about that. Independent source, that is, it contains only resistors and dependent source. Okay. That is, it contains only resistors and dependent source. Combinations. By default, all current and voltages, then what happens is by default all voltage and current, voltage and current in the network are always zero. Are always zero. Why? Because there is no independent source available, right? And it is also called as dead network. Dead network. So you can take some examples. Let us say you can take some examples, like suppose we have one voltage source and one resistors, but the path is open. You can say this is my 5 volt and this is my 1 kilo ohm. So still this is a network, but current cannot flow because having independent source and having a resistor or capacitors and all does not tell you, it is not a sufficient condition that current will definitely flow. Understood? Now let us say it is like this, and one more 5 volt voltage source is there, and even it is closed path. Let us say this is 5 volt, this is also 5 volt, and this is 1 kilo ohm. Still current is not flowing in this. Okay, so this is also not possible. Now let us say only like a closed path is there, but all are only resistors, like let's say 1 kilo ohm, 2 kilo ohm, 3 kilo ohm, 5 kilo ohm, but still there is not possible of having a current flow. I will tell you one more circuit. Let us say I'll give you an example. Resistor is there, one more resistor is there, and then we have like resistor and one dependent source is there. Okay, and then let us say one more resistor is here. So we have dependent source. So you can say that, let us say this is 6 V node, where V node is this one, and this is my 1 kilo ohm, this is let's say 4 kilo ohm, this is let's say 3 kilo ohm and 6 kilo ohm. So still these are actually called as dead network. Okay, these are called as dead network because they are not having any independent source. However, these two are also not having a situation of current flow. Understood? Now let us talk about basic electrical quantities, which is going to be my current, voltage, all this. So we will talk about basic electric quantity. So we'll not spend much of the time because you guys already familiar about all this. So we'll talk about, let us say, current. Current, you know, it is represented by I. Okay, capital I, small I, all these things. So you can tell in a definition that the time rate of change of charge. Okay, or you can say the time rate of flow of charge is called as current. It means what? My I will be equal to dq by dt. It means you are telling that in dt amount of time, dq amount of charge flows. Amount of charge flows. Understood? So I is equal to dq by dt. That is the most important formula for your understanding. So you can keep a box around it. Understood? So I equal to dq by dt. From this equation itself, if we want to find out what is my q, then we will be able to find out very easily what will be my dq. That will be I dt. And if you want to find out my current, the charge, then q will be integration I dt from, let's say, time t1 to t2. So what is the charge that has flown from, let's say, time t1 to t2? That can be very easily calculated by integration of I dt from t1 to t2. And the unit of current, I, is nothing but ampere. Okay, and it is represented by A. Understood? Now let us talk about voltage. So current we have talked about. Now we'll talk about voltage. V. So what it says is actually it is like charge rate of work done. Okay, So it is, what is the amount of energy that is required to move dq amount of charge. So you can say if dw is energy, okay, dw amount of energy required to move dq amount of charge, dq amount of charge from one point to another point in electric field, from one point to another point in electric field. Then we say the potential difference between these 2 points, then the potential difference, or this is also called as voltage, okay, between the 2 points is nothing but your V, okay, which is going to be dW by dQ. So this is the quantity that we are going to find out as voltage, which is going to be energy required to move per unit charge, okay. Understood? And in that case, what is the total energy that is needed? That also can be found out very easily. My dW will be equal to V dQ, and from here my energy will be required. Energy will be required integration V dQ. Understood? Now let us talk about one more important quantity, which is called as energy and power. So energy and power. So what we are going to talk about this energy and power is, let us say to have a non-zero amount of current flow, some amount of energy has to be spent, right? Like we want to have some current, then there will be a need of energy to flow. So we can write it down as, to have a non-zero amount of current, amount of current flow, some amount of energy has to be spent. Has to be spent. And the rate at which the energy is spent, okay, and the rate at which energy changes with respect to time, with respect to time is called as power. It means what? I am going to define a quantity power P as energy spent per unit time, okay, dW by dt. So this is my power. Now you are not familiar about maybe this quantity, so you can also write it down as P is equal to dW by, can we write it down, dQ, and dQ by dt. So this dQ will get cancelled, and you know already that dQ by dt was nothing but my V, and dQ by dt was nothing but my current I. So my power is nothing but what? P equal to VI. Got it? So this is one more important relation which is very, very important. And this is applicable for any kind of electrical network. Okay. This is applicable for any kind of electrical device. So like if you want to find out power, you can very easily see what is the voltage and what is the current, and you will be able to find out the power. That is basically you can talk about like resistor, capacitor, inductors, diode, voltage source, current source, anything you find, you can write down very easily. Power is nothing but voltage into current. And you want to find out instantaneous power. Instantaneous power. Then what we will do? That will be my PT is equal to VT into IT. So it will be time dependent. Understood? That's all. So let us derive some more relations about this power and energy. So why don't we do one thing? What was my power? It was nothing but dW by dQ, dW by dt, right? And this from here we can find out what is my total energy. So W can be written as P dt. Okay. Sometimes we represent it by E, but in electrical networks, E will be used as, let's say, like for electromotive, electric field. That's the reason I'm trying to use W. Okay. Similar to that, I was what? Dq by dt, and from here we found out Q is equal to integration I dt. Similar to that, V was what? My dW by dq, and from here my W can be found out as integration V dq. So we have lot of relations in terms of integrations and differentiations. Okay. And one more important quantity is there for many other branches like electrical E branch or IN branch or EC branch. So people try to ask you like kilowatt hours. So I'll tell you now itself, 1 kilowatt hours is going to be equal to how much? 3.6 into 10 to the power 6 joules. So how do you find out this one? 1 kilo means 1000 into hours. Hours is nothing but 3600 seconds, right? So this is in joule. So nothing but it is going to be 3.6 into 10 to the power how many? 3 plus 3 6. Okay. So 10 to the power 6 joule. This is one important problem. Okay. So while solving any problem, what you have to do is you have to always convert your time into second and obtain the like energy as joule. So this is the energy. Energy, that is W, will be represented in joules, and this is represented by J. Okay. Let us take few questions and try to solve it. So let's say the question is, a 12-volt car battery is connected to a a 36-watt headlight. 36-watt headlight for 1 hour. Understood? Now we have to find out few quantities. First one is find the current passing through the bulb or headlight. Okay. Find the current passing through the headlight. So what is the current that is passing through the headlight? You can find out by yourself as well if you want. Then total energy dissipated. What is the total amount of energy that was dissipated? And next is the total charge passed through the bulb or the headlight. The total charge passed through the bulb. Okay, so this is the question that we have been asked to find. So how shall we solve it? Let's make it our common sense and solve it. We don't have to like spend much of the time here. So what is the voltage of the battery? V is equal to 12 volt, right? And then what is the power of this particular connected to a 36 watt headlight? Means power is nothing but my 36 watt. The unit of power is watt, okay? And let us say it is connected for 1 hour. So my time is 1 hour is nothing but 3600 seconds, okay? So this is how we have found out. Now can you tell me what is the current passing through the bulb? So you know already P is nothing but your V into I, and we have V, we have P. So I we can find out very easily. So my I will be P by V, which is nothing but your 36 divided by 12, that is 3 ampere. So 3 ampere is the current that was passing through the headlight. Understood? Now what is the total amount of energy dissipated? So you know already total energy. If you want you can put it W, or otherwise you can write down E also for energy, not a problem. So E is nothing but integration P dt and time t1 to t2. So since power is constant, okay, and we have 1 hour time that is given, so I can write it down as P into T2 minus T1 is nothing but your 1 hour time. So power is 36 watt multiplied by 1 hour time, that is nothing but 3600 seconds. So 36 into 3600 is how much? 1296, double zero is there, joule. And if you want to convert it into scientific form or maybe kilojoules, then 129.6 kilojoule. So this is the amount of energy that is dissipated. Now the next question that is being asked is, what is the total amount of charge that has passed through the bulb? Okay, so you know already what is the relation that we will utilize to find out that. The charge q is equal to nothing but I dt and the time t1 to t2. So you know already the current that was passing through is I, let us say t2 minus t1. So this will be 3 ampere multiplied by 3600 second. So that is going to be 108,000 coulombs. So q is in coulomb. If you want you can put it in kilocoulomb also. So that will be 10.8 kilocoulomb. Understood? Now since charges are actually electrons, so you can write it down, that will be negative of 10.8 kilocoulomb because of electrons. Okay, understood? Now if you want to find out how many number of electrons, let's say number of electrons, then how will you find out number of electrons? Can you tell me? You know already that electron charge is equal to how much? 1.6 into 10 to the power minus 19 coulomb, right? So my number of electrons, my total q is nothing but n into e. So my number of electrons will be what? Q by e is nothing but minus 10.8 kilocoulomb, right? 10 to the power 3 divided by e is 1.6 into 10 to the power minus 19. And these many number of, this will be negative because e is negative charge, right? Now if you do this calculation, so what will happen? 10.8 divided by 1.6 multiplied by 10 to the power 3 into 10 to the power 19 will go up. So I can take it down as 1696 6.74 into 10 to the power 22 electrons. So these many electrons have passed. Okay. So this was all about this particular question. Let us take another question. Question is, I'll write it in other color. The current entering at a certain terminal with respect to time is as follows. There is a graph given, okay? The current entering at certain terminal with respect to time is as follows. How it is? So there is a graph that is given like this. So it follows like this and then it goes up, then come down and like this. So this is how it tells, and this is my 1, this is my 2, and this is my time which is in microseconds, okay? And this guy is nothing but your current, which is this one is 5 milliampere and this one is 2 milliampere. Understood? Now assuming the current is due to positive charge, assuming the current is due to positive charge, that is protons, determine the number of charged particles, determine the number of charged particles passed through the terminal, passed through the terminal up to 1 second, up to 1 microsecond. So we have to find out what is the number of charged particles that has passed up to 1 microsecond. So basically we have to identify up to this stage, like this shaded area. Understood? So what is the first thing that we'll try to find out? You know already that if we find out what is the charge, then we can find out number of charged particles, right? Very simply. So we can see what is the charge. So that will be I dt, right? And you know already this is nothing but integration. So we can actually my current is actually flow, like varying, right? So either you can find out what is the equation of current and then integrate from 0 to 1 microsecond. That is one method. Another method is current integration is nothing but the area under that curve. So area we can find out very easily. What? That will be area of triangle 1 by 2 into base into height. So that can be written as 1 by 2 into base is 1 microsecond into height is nothing but 2 milliampere. So that will be 1 microsecond into milliampere, that is nano coulomb, okay, or 1 into 10 to the power minus 9 coulomb. Understood? Now number of charged particles, that will be equal to what? N, let us say, is going to be total charge divided by charge on 1. So that will be equal to 1 into 10 to the power minus 9 divided by 1.6 into 10 to the power minus 19 coulomb. So that is nothing but 1 nanocoulomb is 1 into 10 to the power minus 9 coulomb. Okay. So if you solve this 1 by 1.6, so you are going to get 0.624 into 10 to the power 10. So these many charged particles were passed at the terminal up to 1 microsecond. Okay. So all right, you keep up to this, and then in our next session we'll talk about more of our network theory topics. Thank you.